The team proved that CoE compound was capable of killing bacteria in established biofilms while also inhibiting the formation of biofilms. It's a rare 1-2 punch in the world of antibiotics. There are a couple antibiotics that do have anti-biofilm activity, but they aren't used systemically, or they are used systemically but really shouldn't be, which that's like a whole thing. Our industrial agricultural system just pumps all of these animals with antibiotics, and that leads to the resistance. That's what it's talking about right here, is us being really dumb with the tools that we have, all just to make a buck. Moreland said, alluding to the high toxicity of some of these antibiotics. Also, that's another thing, is some of these antibiotics are so toxic that it will literally hurt you to take it. So if we could have something that doesn't do that, that would be great. For example, polymyxins is a topical form, are effective against biofilms, but are toxic to the kidneys at the doses used systemically with IV injection. Polymyxins accumulated in the patient's kidneys, causing damage to the cells and tissues, and severe cases leading to kidney transplants. So you're given an awful option of both the patient and the doctor of either letting the disease or bacteria take its course, which could, ruin your brain or your spine or your muscles or your nerves, or just take your life, might just leave you paralyzed or whatever, or give you this antibiotic that's going to ruin your kidneys, and then you're going to have to be on immunosuppressants the rest of your life and have a kidney transplant. So do you want to, this is literally the choice that people are given in these situations. Do you want to pass away or become paralyzed, or do you want to have your kidney have to be replaced? And if that's what these people just saved these people from doing, they don't have to make that decision anymore because we have this new medication that just came out. That's what these people just gave us. In contrast, the Bazin lab was developed COEs to be highly selective for bacteria. In chemical communications, Moreland and team investigated how structural features of these molecules could drive the affinity for bacterial membranes and antibiotic activity without detergent-like effects. Your cells are pretty good at tolerating soaps and detergents, but other cells in your body, especially red blood cells, are very sensitive, which is why these compounds are only used externally or to decontaminate surfaces, and not as a therapeutic agent. For COEs, they found membrane permeability and antibiotic action are not inherently linked, suggesting a novel mechanism behind COE's activity. And critically, a mechanism that can be highly selective for bacterial membranes over mammalian ones. In fact, the molecules in the MAB experiment were able to reach inside phagocytes to kill the bacteria without damaging the mammalian cells. That is bizarre. They even say, we do not know the exact mechanisms, but we definitely show that CoE kills bacteria and doesn't kill mammalian cells. Just round of applause for them, like standing ovation. And here it says that we're going to learn a lot from machine learning, so they're even going to be bringing in AI into this sort of thing, to into the fight against the bad bugs. Ideally, CoE antibiotics would someday serve as a safe and effective treatment, effective in cases of the most resistant bacterial infections. So we're just going to hold this onto the reserve, to make sure that we have something, because right now we don't have anything for some things. So now we have something, and we're gonna hold this onto the back burner and probably learn how it works, because we don't want to use it if we don't fully know how it works. It might be really sensitive. What if, just hypothetically, use it and we don't know that it could form some sort of resistance that we don't know about. So we use it, and then it becomes resistant to it, and we've screwed ourselves over. We didn't even know that was possible, and we've ruined our only tool that we had, that we could have used, but we didn't use it responsibly. So that's not what we're going to do. We're going to use it responsibly, and we're holding it off. We're not just going to use it willy-nilly. But we probably will start saving lives and organs with it, which is what it's supposed to be used for. And then here we have electrons become fractions of themselves in graphene, study says. The electron is a basic unit of electricity as it carries a single negative charge. That is what you're taught in high school physics, and it is overwhelmingly the case in materials and nature. But in very special states of matter, electrons can splinter into fractions of their whole. This phenomenon is known as fractional charge. It's exceedingly rare, and it can be corralled and controlled in exotic electronic states that could help build resilient, fault-tolerant quantum computers. Today, this effect, known to physicists as the fractional quantum Hall effect, has been observed a handful of times, and mostly under very high, carefully maintained magnetic fields. Only recently have scientists seen the effect in a material that did not require such a powerful magnetic manipulation. So they've only made these with, like, magnets in the past. And basically they stack a bunch of graphene in 5 layers and in different ways, and this 5-layer graphene is a material system that where many good surprises happen. Fractional charge is so exotic, and we can now realize this effect with a much simpler system and without a magnetic field. That in itself is important for fundamental physics, and it could enable the possibility for a new type of quantum computing that is more robust against perturbation. And this is from National Institute of Material Science in Japan. And talking about this fractional quantum Hall effect is an example of weird phenomenon that can arise when particles shift from behaving as individual units to acting together as a whole. This collective correlated behavior emerges in special states, for instance when electrons are slowed from their normally frenetic pace to a crawl that enables the particles to sense each other and interact. These interactions can produce rare electronic states, such as a seemingly unorthodox splitting of an electron's charge. In 1982, scientists discovered the fractional quantum Hall effect in heterostructures of gallium arsenide, where a gas of electrons confined in two-dimensional plane is placed under the high magnetic field. The discovery later went on to win the Nobel Prize in Physics. Those researchers achieved the groundbreaking results using magnetic fields to slow down the material's electrons enough for them to interact. The fields they worked on were more than 10 times stronger than what is typically powers an MRI machine. Wow. In August 2023, scientists at the University of Washington reported the first evidence of fractional charge without a magnetic field. They observed this anomalous version of its effect in a twisted semiconductor called a molybdenum dideleuteride. The group prepared the material in a specific configuration which theorists predicted would give material inherent magnetic effect, enough to encourage electrons to fractionalize without external magnetic control. The no magnets result opened a promising route to topological quantum computing, a more secure form of quantum computing, in which they added ingredient of topography, a property that remains unchanged in the face of weak deformation or disturbances, gives a qubit added protection when carrying out computation. This computation scheme is based on a combination of fractional quantum Hall effect and a superconductor. It used to be almost impossible to realize. One needs a strong magnetic field to get a fractional charge, while the same magnetic field will usually kill the superconductor. In this case, the fractional charges would serve as a qubit, the basic unit for the quantum computer. So that's like very, very in depth, but basically they found a new type of energy that they can run a quantum computer on. That this one little bit of energy will be a qubit. That's what they're calling it. Like a normal computer has a byte. This will be a qubit. Such pentalayer graphene structure is embedded in graphite and can be obtained by exfoliation using Scotch tape. When placed in a refrigerator at ultra-cold temperatures, the structure's electrons slow to a crawl and interact in ways they normally wouldn't when whizzing around at higher temperatures. That's hilarious. At exfoliating Scotch tape at low temperatures. In New York, the researchers did some calculations and found that electrons might interact with each other even more strongly if a pentalayer structure were aligned with hexagonal boron nitride, a material that has similar atomic structure to that of graphene but slightly different dimensions. And that would form a superlattice. And they said that as they applied a current to the material and measured out the voltage, they started to see signatures of a fractional charge where voltage equals the current multiplied by a fractional number and some fundamental physics constants. The day we saw it, we didn't recognize it. Then we started to shout as we realized that this was really big and it was a surprising moment. With further analysis, the team confirmed that graphene superstructures indeed exhibited the fractional quantum anomalous Hall effect. It is the first time the effect has been seen in graphene. Graphene can be a superconductor, so you can have two totally different effects in the same material right next to each other. If you use graphene to talk to graphene, it avoids a lot of unwanted effects when bridging graphene to other materials. We are diving in to explore fundamental physics ideas and applications. We know there will be more to come. So, translate that a tiny bit as much as I can. This is like crazy top of the line physics. This is MIT and University of Japan. Look how proud these people are. Sorry, before I go on, just if anybody's looking at the picture here, the proudest looking group of people. Like, awesome. So proud of you guys. So basically, as much as I can tell, is that there's this graphene that has different abilities, and you can both cut down on the amount of energy that passes through it, as well as supercharge the amount of energy that goes through it in this graphene through this 5-layer material that they added. And then they added this other super lattice type of thing that like connects it all together even more, and suddenly you can have, like they said, right next to each other in the same material, something that is causing the energy to spike, and then right next to it causing the energy to dip. So that's not easy to do, but they found out a way to do it. All right, and apparently we have found out some of how whales communicate. That we have finally solved the mystery of how whales sing underwater, new study says. And I had clicked on The Atlantic originally, and they started off the article with this question. It's like a rhetorical, hypothetical type of thing that says, if we can learn to speak their language of the whales, what should we say? And like, oh boy, guys, that was like a punch in the stomach to me whenever I read that for the first time. What should we as humans tell whales if we had the ability to talk to whales? What would we tell them? What would be the sentence? The only thing I can think of is, I am so sorry. I am so sorry for the generations that have suffered at the hands of humans, and that we make so much noise that you can't think or talk to each other, and that not all humans are like that, and that we have fought for you guys, and that not all humans are like that, and I'm just so sorry. That's what I would tell the whales. I'm so sorry, guys. Not everybody's like that. So we found out that within the animal's respiratory tract, they evolved nasal and oral plugs to protect the airways from water when breathing and feeding. Scientists learned that air sacs evolved to allow the baleen whales to recycle air while creating vocal sounds. To conduct the study, which was led by Cohen Elmans, a professor at the University of Southern Denmark, the team of researchers obtained a mink, humpback, and sea whale soon after they had died, and removed their larynxes to study them in a lab. in a way so that no level of analysis has ever done before. He and his team created computer models of the whales' voice boxes that simulated certain aspects. We now figured out how whales have been able to successfully communicate with each other under the water. And this evolved probably like 40 million years ago and has allowed the whales today to be successful. The new study also revealed while the noise that humans make in the ocean is so disruptive and harmful for the animals. The whale's laryngeal structure have physiological limits to the frequency range and depth of their songs, making it difficult for them to communicate when there is loud noise. Sound is absolutely crucial for their survival because it's the only way they can find each other to mate in the ocean. Elements told CNN he hopes that finding this new study can help mitigate the noises that we make so that whales can better communicate with each other. So now that we found that out, maybe we'll do something about it. Ellen Coombs, a Peter Buck postdoctoral fellow at Smithsonian National Museum of Natural History, who was not involved in the study, noted a statement to CNN that human-made noise presents a considerable challenge to whales. Many baleen whale populations are starting to increase thanks to the ending of commercial whaling, but it looks like these magnificent animals are now dealing with the next man-made challenge, and that is noise. Ellmans told CNN the study that it's just scratched the surface and that it only involved young animals. Therefore, he and his team hope to study adult whales to delve deeper into their findings. So hopefully we'll be able to do something about that. That's pretty rough. I know there's so much going on in the ocean and stuff, but at least we're like, some people care, you know, and they're starting to do stuff about it. I'm gonna try to skim through some of this stuff. I don't know how much I'll be able to skim through, but it is worth mentioning and reading through. It's not super long, but this is from February 14th, and just kind of goes into, again, that we don't know much about much. And we talked about the paradox of knowledge the last time. This kind of fits into this, but in a funny way. There is now new addition to the magnetic family. Yeah, that's right. New type of magnetism. So yeah, new type of magnetism just pops out like it's nothing. Absolutely mind-boggling. The experimental discovery of this new branch of magnetism is reported in Nature and signifies new fundamental physics and major implication for spintronics. Magnetism is a lot more than just sticking things to the fridge. This understanding came with the discovery of antiferromagnets nearly a century ago. Since then, the family of magnetic materials has been divided into two fundamental phases: the ferromagnetic branch, known for several millennia, and the antiferromagnetic branch. The experimental proof of a third branch of magnetism, termed Altermagnetism, was made at the Swiss Light Source SLS by international collaboration by Czech Academy of Sciences together with Paul Scherrer Institute of Psi. The fundamental magnetic phases are defined by specific spontaneous arrangement of magnetic moments or electron spins and of atoms that carry the moments in crystals. That blows my mind. I'm trying to put that in my mind, and it's very, very difficult. The fact that they even call this measurement a magnetic moment is such a weird term. Alright, so I had to go and look up what the definition of a moment was in magnetism and mathematics. Apparently it goes back to Archimedes, way back in time. Once again, the philosophy of the past helps us today and in the future, that in mathematics and physics, a moment has a meaning distinct from commonplace sense of a moment of interval of time. It's a shortened form of momentum and typically involves two different dimensions or kinds of units multiplied together, as momentum is mass times velocity. In particular, It is used to describe things related to torsion or twisting forces. Thus, we have magnetic moments, dipole moments, moments of inertia, and so on. And that was from Barry Gimm, Assistant Professor of Chemistry, Biochemistry. And that was the answer that I felt was the clearest. Ferromagnets are the type of magnets that are the type that stick to a fridge. Here spins point to the same direction, giving macroscopic magnetism. In antiferromagnetic materials, spins point in alternating directions, with the result that the material possesses no macroscopic net magnetation, and thus does not stick to the fridge. Although other types of magnetism, such as diamagnetism and paramagnetism, have been categorized, these describe specific responses to external applied magnetic fields, rather than spontaneous magnetic orderings in materials. Altermagnets have special combination of the arrangement of spins and crystal symmetries. The spins alternate as antiferromagnetics, resulting in no magnetation, yet rather than simply canceling out, the symmetries give an electric band structure with strong spin polarization that flips in direction as you pass through the material's energy bands, hence the name altermagnets. This results in highly useful properties more resemblant to ferromagnets, as well as some completely new properties. This third magnetic sibling offers distinct advantages of the developing field of next-generation magnetic memory technology, known as spintronics. Whereas electronics makes use of the charge of electrons, spintronics also exploits the spin state of electrons to carry information. So once again, talking about electrons to carry information, like what and a new method of carrying information with electrons. Once again, you have to reflect back to the whole consciousness magnetic effect on the brain and interaction, that somehow these electrons can carry information between the magnetism of the earth and other things and our brain, and somehow they're interacting. We don't know how exactly, well, at least the public doesn't exactly know how it's interacting, but here we have a new type of interaction between electrons that are spinning that can carry a new information differently than we previously knew. Whereas electronics, how you're listening to it now, is just a flow of electrons. Apparently they have this new type of thing where they spin the electrons in a particular way that causes information to be stored and transmitted differently. So that's just, it's hard to wrap your head around this stuff, but you have to, because it's only beginning. This is just starting to change everything, because these things it's like a snowball. Once it starts rolling down the hill and starts picking stuff up, it gets bigger and bigger and bigger and bigger, and then all of a sudden you're down at the end of the hill and you get hit by this giant avalanche, and you didn't see it coming because you weren't paying attention. So this is the beginning of the snowball rolling down the hill. Although spintronics has for some years promised to revolutionize IT, it's still in its infancy. Typically, ferromagnets have been used for such devices as they can offer highly desirable strong spin-dependent physical phenomena. Yet the macroscopic net magnetization that is useful in so many applications poses practical limitations on the scalability of these devices, as it causes crosstalk between bits, information carrying elements, and data storage. More recently, antiferromagnets have been investigated for spintronics, as they benefit from having no net magnetization and thus offer ultra scalability and energy efficiency. However, the strong spin-dependent effects that are so useful in ferromagnetics are lacking, again hindering their practical applicability. Here enter altermagnets, the best of both worlds. Zero net magnetization, together with the coveted strong spin-dependent phenomenon typically found in ferromagnets, merits that we regard it as practically impossible. That's the magic about altermagnets, says somebody from the Institute of Physicists, Czech Academy of Sciences, principal investigator of the study. Something that people believe was impossible until recent theoretical predictions shows it is in fact possible. So we thought it wasn't possible, and then it is possible. All of a sudden, in 2022, the theorists published their predictions of the existence of magnetism, altermagnetism. So 2022, they predicted it. The proof came using spin-angled resolved photoemission spectroscopy. The proof came using spin-angled resolved photoemission spectroscopy. This technique enabled the team to visualize a telltale feature in the electronic structure of a suspected altermagnet. The splitting of electrical bands corresponding to different spin states, known as the lifting of Kramer's spin degeneracy. This discovery was made in crystals of manganese telluride, a known simple two-element material. Traditionally, the material has been regarded as a classic antiferromagnet because the magnetic moments on neighboring manganese atoms point in opposite directions, generating a vanishing net magnetization. I feel like I'm like casting a spell with these words right now. This is like so hard for me to pronounce. I am not a scientist. However, antiferromagnets should not exhibit lifted Kramer spin degeneracy by the magnetic order, whereas ferromagnets or altermagnets should. When the scientists saw the lifting of Kramer's spin degeneracy accompanied by the vanishing net magnetization, they then knew they were looking at an altermagnet. Now that we have brought it to light, many people around the world will work on it. The researchers believe this new fundamental discovery in magnetism will enrich our understanding of condensed matter physics with impact across diverse areas of research and technology. As well as its advantages to the developing field of spintronics, it also offers a promising platform for exploring unconventional superconductivity through new insights into superconducting states that can arise in different magnetic materials. Altermagnetism is actually not something hugely complicated. I just have to laugh because I've been struggling with this. I'm sure some of y'all are also struggling with this. Magnetism is so hard. But it's involved in like everything, like all aspects of our lives. So trying to understand it is really important. Altermagnetism is not actually something hugely complicated. It is something entirely fundamental that was in front of our eyes for decades without us noticing it. Again, that sounds exactly, I keep on saying this over and over and over. Something entirely fundamental that was in front of our eyes for decades without noticing it. And it's not something that exists in only a few obscure materials. It exists in many crystals that people simply had in their drawers, and in that sense, we've brought it to light. Many people around the world will be able to look at it, giving potential for broad impact. So he's literally saying we just had this lying around everywhere and we couldn't look at it. We didn't know how to look at it. We've talked about that I gave the traffic law example last episode. We've talked about that with the obelisks. I'm sure the soil example too. I mean, it's just endless, like that we have all of this information in front of us. We just don't know how to articulate it in ways to find the answers that we need to find. And we're starting to. And that's the point of this podcast and all of this stuff that I'm pointing out here, that we're starting to figure this stuff out. And we had it in front of us the whole time. We just needed a different perspective. We needed some new people to come in and look at it differently. And here we have Coast Guard rescues man in water off Florida Keys. The Coast Guard rescued a man in the water near Wisteria Anchorage in the Florida Keys early Sunday morning. The man fell into the water while attempting to board his dinghy from his sailboat when the dinghy capsized. Fireman Nicholas Leake, aboard a moored Coast Guard cutter, Thetis, heard someone cry out for help in the water around 2 a.m. Leake contacted Coast Guard Sector Key West, who was issued an urgent marine information broadcast, and launched a crew from Coast Guard Station Key West to rescue the man. The man was found clinging to a rope connected from his sailboat to the dinghy. Upon being rescued, he stated he'd been calling for help for over an hour, and the man was transferred to an awaiting EMS in stable condition. Due to the vigilance of Fireman Leake and his keen hearing, we were able to successfully rescue the mariner. This is a great reminder that as the warmer months roll in, mariners should maintain boating safety precautions, wearing life jackets, and keep emergency position indicating radio beacon on board and a secondary noise-making device, such as a whistle, to call for help. Yeah, if this guy had a whistle, it would have been way easier. But one thing that this Coast Guard did not note is trying to get into the water or a little tiny dinghy at 2 o'clock in the morning. Like, don't get into the water in the middle of the night by yourself. All these people that are getting stranded and stuff, a lot of them are by themselves and they're doing dumb stuff. And I would consider getting in the water on a dinghy at 1 a.m., midnight, whatever, whenever he was doing this, is kind of dumb. I bet alcohol was involved. I would bet that. But y'all try to be safe and don't go wandering into the woods or mountains or the middle of the lake or an ocean by yourself in the middle of the night, or 90 mile an hour, -9 degree weather. All of those circumstances, just stay inside, wait it out, go out and swim in the lake in the morning like a regular person. You're going to get hit by a boat. I mean, the guy's lucky he didn't get hit by a boat out there floating in the water. All right, be safe, everybody. You can email me at inspiredearthpodcast@gmail.com if you have any articles or anything you wanted to share. I appreciate that. Be safe, everybody.